Welcome to episode 13 of the Welding Codex. This is a podcast for those who want to learn more about the technical side of welding and materials joining. We try and talk about welding codes, welding defects, metallurgy, and subjects along those lines. Today I have a special guest, Elaine Thomas. Elaine began her career at a foundry on the West Coast in 1977, where she spent almost 4 decades working and managing operations in the melt shop, welding engineering, heat treating, chemistry, and mechanical testing labs. Thomas is considered one of the utmost experts in metallurgy, and she currently serves on multiple committees, including the SFSA Specifications Committee, SFSA High Alloy and Heavy Sections Research Committee, ASTM A01.18 Subcommittee for Cast Steel. Elaine is also a great lecturer and gives presentations on subjects such as post-weld heat treatment of thick ferrous castings. And she does this at any number of conferences. You might see her listed every now and then on some of these AWS websites or, speaking at one of these big conferences. She's a heavy hitter. She's very knowledgeable about duplex stainless steels and other high alloy casting materials. Before we get into our conversation with Elaine, time for the advertisements. If you're on a budget and looking for an affordable online training course for the AWS CWI inspector exam, visit train-eng.com. train-eng.com. And check out the online courses for Part A, General Knowledge, and Part B, the Hands-On Inspection. Train-eng.com also has some buffet-style options that are different from some of the competitors on the CWI review course. If you only want to take a certain snippet of the course, the review course, you can do that. If you want to take the part on metallurgy or metrics or safety or whatever, they've got it broken out into a buffet style so you can pick and choose. If you're strong in one, they're not going to make you sit through the whole thing. There's also a CWI question bonanza with only practice questions, so you can just do practice questions to your heart's desire. If you like what we're doing here, feel free to make a PayPal donation on my website, texasweldingengineering.com. Also check out my YouTube channel and the material posted on that platform. All right, let's get into the conversation with Elaine. Welcome to the Welding Codex. We're here today. I've got Elaine Thomas, a good friend of mine, and I worked with her years ago for an employer out on the West Coast. On the West Coast, it was a foundry. We worked together. We did a lot of, the foundry that we worked for did a lot of really off-breed, off-color, interesting alloys. It wasn't just, a carbon steel type of foundry. We did stuff that nobody else could do and a lot of really weird things like, pump casings made of duplex stainless steel that are the size of a Volkswagen and things like that. So anyways, hello, Elaine. How are you doing today?
Good morning, Gary.
So Elaine, how did you get into metallurgy? Where did you go to school? I know the answer to this. Go Cougs.
Yeah. Same school you went to. I went to Washington State University. I graduated back in 1976. I was the first woman to graduate from the Material Science and Engineering program. That's my big claim to fame, which is a pretty good deal because Kaiser Aluminum helped me with scholarships, so I was able to get out of college with no debt, which was a great thing. We had a very small class. My first job was working for Battelle Institute out at Hanford. I was a garbage man. I worked on nuclear waste vitrification, nuclear waste disposal, turning it into glass. And then a job came up in Tacoma at this foundry, and I stayed there for about 40 years. I've always kept in contact with the college and the Society of Women Engineers, and I tended to try and get a person to mentor each year, and it involved, emails and just making sure they didn't leave the major. A lot of women, we lost them somewhere along the line, and a lot of it was because there weren't many of them, so it was important to build a community for them to bounce their ideas and feelings off of, and for them to know that there's maybe jobs out there waiting for them.
I kind of was going to steer it in that direction of mentoring young engineers, because I noticed that's one thing when we worked together, you tended to have usually an intern, or they would hire your replacement or something along those lines. There was always like something in the pipeline. You seemed to, because you were such a trailblazer as far as being the first woman to come out of that university in that program, you were the trailblazer for a lot of the people that followed you. So I noticed that you, instead of just saying, all right, it's mine, I conquered the world or did whatever, you were always giving back to others and trying to, you put a lot of energy into helping other people try and achieve the success you had achieved professionally.
Thank you. That's very nice. I do think I would have made a good teacher. I think I've always enjoyed being a speaker at a lot of like AWS meetings and ASM meetings and Steel Founders Society meetings. I've been a speaker for many, many years, and I taught part of a quality control program at South Seattle Community College for about 10 years or so, a little less maybe, and that was a lot of fun. So falling into having an intern was just the next step, and I had, I don't know, maybe 5 of them or so, really nice kids right before their senior year in college, and they helped me and I learned a lot from them. That's true. But it was a really fun experience. I enjoyed it immensely.
I was going to tell this story, or at least kind of line something out. When I worked with Elaine, a lot of times we'd have these conversations with people from, the oil companies, the big oil companies, and we'd be online and have these conversations with PhDs and whatnot, and they'd be getting on our case about something to do with the chemistry and with the castings or whatever, the duplex. And Elaine can go from the conversation she's doing right now, this demeanor she has, and she throws a switch and it's just like game on, and she's just on point. Okay, and that's why we do the sigma phase, and then and it's just like, wow, where'd that come from? And then she'll throw the switch back and she'll be in the demeanor she's in now, just kind of conversational chit chat. But I always like going into some of these meetings, these online meetings with her, with these PhDs, because it's like, okay, Elaine's got my back. All right, we're good to go. So anyways, that's why I really enjoyed working with Elaine over the years. That being said, Elaine, let's talk duplex stainless steel. Where did this duplex stainless steel come from? Everybody knows about austenitic and ferritic and the other flavors. Where did duplex come from?
Well, I'll tell you, it turns out that salt water for austenitic stainless steels is the Achilles heel of austenitic stainless steels. Salt water will devour austenitic stainless steels. It doesn't do well at all. I realize it's been used a lot, but it doesn't really hold up as long as it should, okay? So there was a need for something that was a lot more resistant to salt water. So in the 1950s, 60s, at Ohio State University, I'm supposed to say the Ohio State University, Mars Fontana, who was a welding engineer, metallurgist there, started to take the alloy CD7Cu-1, which is a pH hardening stainless steel. It's the one with the copper, 2.5 copper, 4-5 nickel, and a lot of chrome. He took that alloy and started tinkering with it, and he came up with duplex stainless steel. However, he had no way of injecting nitrogen into it. In fact, I'm sure he didn't even know you could or needed to. Anyway, it turned out to be a real difficult alloy to produce. Casting, forging, whatever. Very difficult. And it wasn't until the AOD, which is called the Argon Oxygen Decarburization Vessel, it's a way of refining steel by blowing argon through it and doing a lot of thermodynamics. Anyway, it's a way you can actually juice nitrogen into the liquid metal. And that turned out to be a wonderful thing. I believe the foundry or the institution that came up with that was in England, and they were called Langley, and they called the new alloy beryllium. And beryllium had a trademark on it, and people would pay a certain amount of money to produce beryllium, and they would get technical help from this Langley. Anyway, all this happened in like the late 70s, and the more people who got AOD vessels and could refine steel and put that nitrogen into the duplex, the more different duplexes appeared on the market. I've been involved with ASTM, American Society for Testing Materials, and the specifications that deal with duplex just exploded with different alloys during the 80s. One of the ones I had a hand in helping to develop was the ASTM A890 grade 5A. That's sort of the general spec. The pressure vessel spec is ASTM A990 grade 5A. Those are called super duplexes because they're a little bit more resistant to salt water when the temperature gets a little warmer. So there ended up being duplexes, and there ended up being super duplexes. And again, the big challenge was getting that nitrogen into the matrix. This made it be weldable, castable, formable. It was the big deal with duplexes.
Okay, so we have, when we're talking duplex, part of our matrix is austenitic and the other part is ferritic, right?
That's correct. The matrix is ferrite, and there are
that's
pools.
giving us some strength, correct?
Correct. You're going to have a strength up around 65 KSI, and some alloys maybe as high as 70 to 75 KSI. The pools are austenite.
Right, and then we're getting kind of the best of both worlds. We're getting a corrosion resistance that'll stand up to a brine or a saltwater situation, but we're also getting strength and more strength at an elevated temperature that we wouldn't be able to achieve with an austenitic or a super austenitic stainless steel.
Well, it's not really used at elevated temperatures. It's usually used at 50 degrees centigrade and lower, more like earth temperatures, okay? It's not really for anything high temperature. So that's kind of important too. A lot of the oil wells might be working up around, 40 degrees C or 50 degrees C, and that's pretty tough even for a duplex. But at 20 degrees C, most of them can do a good job of resisting corrosion.
And this all came out of a guy at The Ohio State. He was working on a precipitation hardening, and then that's the direction it went.
Yes.
And then you've been dabbling with it ever since.
Yes. I've been working with, we worked a lot with Lincoln, Damian Kotecki. He helped develop the weld filler metal for the super duplexes. He was AWS president for a while there.
Yeah, really sharp guy and a really nice gentleman.
Really nice guy. He had kind of a Dear Abby column in the Welding Journal. You sent him in with your problems and he would help you. Yeah, great guy.
So as far as like castings, I just remember we did some just monstrous castings out of the duplex for like pump housings and valves and whatnot. What are some of the difficulties that you ran into in the early years trying to cast this stuff?
Okay, I've split some of those big ones right in half, and it's not pretty. Not pretty. Because there's so much nitrogen in this alloy, you have to be very careful to limit the amount of nitride formers in it, such as aluminum. And since the AOD uses aluminum as a fuel to actually heat up the molten metal. Again, there's a lot of thermodynamics involved there. You can end up with a trace amount of aluminum that might not be so trace, and you can end up with aluminum nitrides, and that baby can just rip that part in two. It's like making a piece of Chihuly art glass that didn't get tempered. It just shatters, okay? Not good. The other thing is that as the part cools in the mold after being poured in whatever form it is, the metal is going to spend a lot of time between the temperatures of, say, 900 and 1700 degrees. During that time, the molybdenum in the alloy, and there is around, let's say, 2-3% molybdenum, some of them maybe even more, but that molybdenum is going to tend to cause the ferrite, which is the matrix, to form a phase, a precipitate called sigma phase. And it basically turns the entire matrix into glass. I mean, it's very brittle. So that when the casting or the forging billet comes out of the mold, it is extremely brittle. Now, the investment people, investment castings, small little things, they don't have that problem. It tends to, those little castings, the kind of thing you can hold in your hand, they cool so quickly in their little shell molds that they hardly have any sigma at all in the as cast condition. And the people can work them and take the risers off in the gates and off they go, and there you go. But if you've got a thicker section, and I'm thinking, I don't really know what the section size is. It has to do with cooling slowly and its time at temperature. But if it's more than a couple hours in that 900 to 1700 zone, you're going to end up with a lot of sigma. So the very first thing that has to happen before that casting gets touched with heat is that it has to be heat treated, given a solution heat treatment, which is taking it up to 2075 degrees Fahrenheit and soaking it until the sigma has dissolved, because sigma hates that temperature. It breaks back up into the individual atoms, and then you water quench it to freeze that atoms out there and not let them reform into sigma. That's such an important step, super important. If you don't do that, the casting won't live to see tomorrow.
Well, and I was going to say with that heat treatment sequence, if none of you have ever seen this, it's kind of crazy because you're taking a casting a lot of times it's the size of a Volkswagen, and they take it out of these ovens, and it's just these heat treat ovens, and it's just glowing red, and they'll have it on a forklift, and then they'll dump it into a quench tank that's about the size of a swimming pool. So you're chunking this Volkswagen-sized glob of glowing orange metal and throwing it into this swimming pool sized body of water, quenching whatever, and it'll bubble. And it's kind of an Old Testament like scene to behold is what she's talking about, because there's steam and fire and brimstone everywhere, but kind of interesting to see. But gets back to, like you say, locking that matrix in place where you want it and without that sigma phase.
Correct. Once you get rid of that sigma phase, you can start to work with the casting, because now it has ductility, it has strength. You can start putting a torch to it to carve off risers or whatever superfluous pieces are on it, and to work with the casting. I always required the duplex castings to have a second heat treatment. The second heat treatment helps the yield strength increase. It usually was a post-weld heat treat type of a situation. Again, you take it up to about 2075 Fahrenheit, and then a couple hours before you take it out of the oven, you lower the temperature down to around 1925 Fahrenheit so that you're quenching from a lower temperature. You let that 1925 stabilize, and then you throw it in the drink and quench the liver and lights out of it. and you can get a higher yield strength by doing that. This is actually in the ASTM specifications in the heat treating. It actually tells you to do this and gives you minimum temperatures at which to do it.
When I started with Elaine, I just thought castings came perfect. I didn't realize that when you get a casting and you break it out of the mold and all that stuff and you chop off the risers, that there's going to be some repair work that's needed. So usually when you're getting a casting, there's been hours and hours and hours of welding put into, there might be porosity or cracks or some kind, the metal didn't go where it was supposed to inside of there. So you spend a lot of time grinding, air arcing, cleaning up these castings, and then putting metal back in. And then that's what she's talking about, this post-weld heat treatment, where you send it back over to the heat treat people. They take it up to the 2075 and then do whatever in the post-weld heat treatment zone. And then you clean up the casting and send it on.
You're right about that. We've been working in ASTM to get rid of the phrase repair weld, which infers that there was something wrong with the casting. The welding and grinding that you mention is really actually part of the casting process. So we're trying to go back to the phrase production welding. How about that? And I think that's really the correct phrase to use.
Right, because it's not like the part had been out in the field in use and something was wrong and you were fixing it.
Right.
You're just using a different process to add material to where maybe it didn't flow when it was originally supposed to go there.
Right.
It's an interesting thing. When do we get the sigma phase in welding?
Again, it's if you're doing a really large weld, especially a large weld, and again, you're really putting a lot of temperature into the weldment, and for a long time. Again, it's a time at temperature. This whole process happens quite rapidly in the 1100 to 1600 degree range. And if it's a couple of hours, you're going to get a lot of sigma again. So if you can keep the temperature during the welding and the interpass temperature real low, and I'm talking low, well below 400 or 500 degrees, then you can keep the sigma from forming.
My professional universe, you're always harping on welders. Okay, preheat this, preheat this, preheat this. With the carbon steel materials, and let's say something that's a high strength carbon steel or something with a little more carbon in it, and then you switch over and then you've got them welding on duplex stainless steel, and you're like, whoa, 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 whoa. Dude, that thing is more than 200 degrees or 300 degrees. Why are you striking an arc on it? Just sit there and don't touch anything until that thing is under a couple hundred degrees.
Right.
And I was going to say, too, when we'd qualify some of these procedures at the foundry, these welding procedures, we'd use some 8 or 10-inch thick test coupons. And I'd have a guy welding there for like a week straight. And they'd run one weld pass, and then they'd sit there for 20 minutes. Because once these blocks, these test coupons would get up to heat, this material doesn't have a very high coefficient of thermal conductivity. It's not like aluminum where it just sheds heat. It's the flip side where this stuff just soaks it up and keeps it.
That's interesting. I didn't really realize that.
Yeah, so those guys would just be over there for a week or so just welding and welding and welding, and you're just like, dude, stop. If it gets above a certain temperature, which goes against everything they've been taught since the time they were in junior high or vocational school. So let's say I'm welding some duplex tubing for whatever situation, thin wall tubing. My chances of getting sigma formation are greatly diminished on that, aren't they?
Yeah, yes, they are. That's going to just cool off so quickly that there really is very little likelihood that will form.
So if I throw a little nitrogen in a back purge on like a tubing weld, is that going to help my...
Sure, that'll help. Because of the austenite phase being face-centered cubic, the nitrogen tends to fit, it's called interstitially, in between the atoms of chrome and moly and nickel and iron. And the nitrogen fits in there very nicely. It doesn't supersaturate and it doesn't form bubbles.
Okay, let's talk about the G48 testing. What's the G48 test get me?
G48 testing, in my opinion, is really something you would do to say, this is what this alloy is capable of doing. I've seen a lot of people use it to qualify a heat or a heat treatment of a part, and there are many different practices in there. All of them are pretty hairy. I think probably using it as a test, like method A or B as a test for the weld and heat affected zone, is probably a legitimate use of it, because you can tell whether you've gotten rid of the sigma phase, or if you can tell whether, if you're doing a no post-weld heat treat, you can tell whether you have a lot of sigma phase in your weld and heat affected zone. But as far as proving a heat is good or bad, I don't think it's such a good test, mainly because if you have, it's based on weight loss, and if you have even a smallest little inclusion or something fall out, your weight loss like jumps through the roof. And I guess that's a problem too with welding. If you have a little bit of slag in there and it falls out, it's going to be a real bad test, and you're going to end up spending a lot of money. So the material has to be really clean that you use.
So what's your favorite alloys to deal with? Nickels, carbon steels? What did you
Oh,
really enjoy casting or dealing with? Or
the duplex is very interesting, I think, and there's a real need out there for those kinds of alloys. Ca6NM, which is a 12 chrome 4 nickel half moly type of alloy, is extremely interesting and is used everywhere. The very first stainless steel that was ever invented was like a Ca15. It's like a 400 series stainless steel. It's like 12 or 13% chrome. It's what your silverware at Denny's is made out of. Back in the 60s, a company named George Fisher over in Switzerland started adding nickel to it, and this alloy Ca6NM came along. They added a little moly as well. A lot of the oil people use this alloy for pumps, and especially there in one form you make it a little softer under a Rockwell C23, and it's really good for hydrogen sulfide, which is odorless, colorless, and kills you in 10 seconds. So, and it's real hard on steel. That hydrogen sulfide just attacks and corrodes it really quite rapidly. So that alloy, in its two different forms, one soft and one a little bit harder, has been used in so many applications, and there are continually questions about how to make it and how to make it well. I've enjoyed that.
so I'm gonna go full circle back to and talk about austenitic stainless steels and sensitization we're worried about there. For those of you that haven't dealt with austenitic stainless steels, if you have your inner pass temperatures too high and this time at temperature thing, you're going to get a thing called sensitization, right, Elaine?
Correct. For every 6 carbon atoms you got in the vicinity of the heat affected zone, it's going to take 23 chrome atoms out of commission and form a C6 chrome 23 precipitate on any kind of grain boundary. This makes the area next to the grain boundary be depleted in chrome, and then out in the main grain you've got the regular amount of chrome. So what you end up with is two different alloys essentially connected by, well, it's a galvanic cell is what it is, right? And so it's very easy for corrosion to just eat right through the material, going for those chrome depleted zones. And that's what sensitization is. And to fix it, you take the metal up to about 2000 degrees. Again, chrome and carbon hate each other at that temperature. They break up. The chrome goes out there and to fight corrosion in the matrix, and then you throw it in the water and freeze it in place. Don't let it form again.
Another workaround is low carbon. If you don't have carbon there, so that's why you'll see these materials that are like 308L or 316L or 3 whatever L.
The L just means that the material has an O3 carbon max, where normally the alloys will have an O8, but the sensitization, those little precipitates, are always C6 chrome 23s, okay? They are always that, okay? It's just that there's less carbons, so they're going to tie up less chromes.
Right. But yeah, there's just less carbon there to tie
Yeah.
up those 23 chromes.
Right.
So instead of having 32 chocolate chips in the cookie, you're only going to have 6.
That's
or
right.
whatever.
That's right. That's right.
Well,
It's just there's fewer precipitates.
And usually it doesn't happen in the weld, it happens in the heat affected zone.
Yep, that's
So
right.
you'll see some terrible pictures where the weld will just fall out. It's like a wedding ring just falls out of a piece of pipe or whatever. What do you think? What else you want to cover today?
I think that's pretty good.
You think we've hit it good enough?
Yeah.
All right. So
it's long enough for people to listen to and go, ugh, blah, blah, blah.
yeah, everything I never wanted to hear about duplex stainless steel. So, all right. Well, we'll call that good, I guess.
Yay. Yeah,
All
we
right.
did a good day.
All right.
Thanks, Garry.
Hey, thanks a lot for stopping by, Elaine. We'll have to do this again. I'll have to get a better script, or you tell me what you want to talk about or something if we decide we want to give this another roll. So
Okay.
I appreciate you taking your time out of your day.
It's good to see you. Say hi to the family.
All right, you too. Say hi to the husband. Take care.
Thanks for listening. Hope this podcast was worth listening to. We're going to have more content coming out. Also, if you want to shoot me an email, gpacex@gmail.com. Give me some ideas, or maybe there's some questions that you'd like me and Pete or me and Joel to answer in regards to welding codes, filler material, or any other material joining question that you might think we have a shot in hell of answering. Anyways, thanks for listening. Take care. Peace out.